Hi, welcome everyone. My name is Udayan Kanade. I have been a mathematician for 25 years now. For 20 years, I've run my own company that does computational mathematics. This is a conference on computational intelligence. Computational intelligence, also known as AI, is going big, and these are exciting times, as we all know. And so I wanted to think about what is the future of computational intelligence in general, and specifically, I'm going to concentrate on computational linguistics, which is natural language processing. To understand how, uh, to understand the future of computational linguistics, we are going to have to go into the past and also have to go to another field first, right? Because that's the only way you can use analogies from another field. And so I'm going to go to the field of astronomy. Uh, Hipparchus was an astronomer, philosopher, lived more than 2000 years ago. And he came up with a model. Astronomers knew that all stars are rotating at that fixed speed, except there are these 5 or 6 star-like objects which seem to be doing something different. We call them planets now. And the thing that people wanted to develop was to develop a model of how those things are moving and can we predict how those things are moving. And Hipparchus was interested in it. And he came up with something known as the epicyclic model, which is basically, using data, he tried to build this model. Imagine more than 2000 years ago, using data, he tried to build this model that, oh, the planets are moving around in circles, but not really exactly circles. They are moving around in circles on top of circles. Okay. And that was his model, Hipparchus's epicyclic model. And then came Ptolemy, and Ptolemy said, no, no, it's circles on circles on circles. And, lots of different astronomers all across the world, including Indian astronomers, came up with their own more and more complicated models to try to predict precisely what these planets are going to do. And it was a very difficult task. Of course, why were they doing it? Astronomy and astrology, today we separate these fields, but at that time they were the same field. And they were trying to say that, oh, if you know how these planets move, then you will also know about your future and your fate, because you will know what the planet is going to do in the future. So I can predict in advance when you should be doing a certain thing. I sometimes find it a little odd or interesting that each these scientists were so advanced as to be able to build precise models of planetary movement using data. How come they were also doing astrology? And the one possible answer is they were doing it for funding. And you're an academic audience, you know that you have to do something for funding. And what do you tell the king? You tell the king that, oh, king asks you, but why should you be studying these 7 moving objects? Oh, because if you study these 7 moving objects, I'll be able to tell you, when to go to war, to reduce taxes or increase taxes. I'll be able to give you good advice about all of this. Now, that's a little reductive. I think there's a better explanation of why astronomy and astrology was related and now is considered 2 separate things. And that is the idea of correlation versus significance. See, both astronomy and astrology work on data, and data will always show correlation. If Mars is going retrograde and you had a cough at the same time, data will say that Mars going retrograde causes cough, right? Our modern ideas of statistical significance developed by people such as Neyman and Pearson, for example, and many others. It's still a rich field of development. Our modern ideas of significance are what now allow us to say that, oh, one of these things is much more significantly a valid correlation, while another could possibly be a hallucination, right? To use a modern terminology, could be a hallucination. We do not actually have enough information. We do see a correlation, but we do not have enough information to to know whether that correlation is actually a significant correlation, really is a scientific correlation, or is a spurious correlation coming out of some vagaries of data. Okay. By the way, I do not mean to say astrology is not a science, but if anyone of you wants to be a scientific astrologer, I would suggest that use modern statistical techniques like significance, like p-values, and like confidence intervals. And if your methodology passes all of these tests, then you can say astrology is scientific, right? So anyway, so coming back to Hipparchus's epicyclic model and Ptolemy and Aryabhatta and all these people's improvement to that model, not many, I'll say 1,000 years later, this another scientist came. His name was Kepler, and Kepler came up with this idea that, oh no, they are not circles and circles on top of circles and circles on top of circles on top of circles. They are ellipses. And their ellipses, the orbits are elliptical, and the orbits are not actually uniformly being moved through. Right? You might remember this from school, Kepler's 3 laws of planetary motion. And so now it turned out that fit data beautifully. Now, here's the problem, right? The earlier model also fit data well. The new model also fit data well. So, should the new model be preferred over the earlier model, and why? This is going to be important to us when we start thinking about artificial intelligence, machine learning, all of these things. So, it turns out that the original model of cycles on top of cycles on top of cycles can be explained in modern terminology by something known as the Fourier series. Anything that is a periodic movement can always be represented by circles within circles within circles. And today we call these circles e raised to I omega t and make a summation, and so it works. So when Hipparchus was building his epicyclic model, he thought that he was using circles because they are the perfect geometric shape, and God must have designed the universe using circles. Okay. Today we realize that that's not true. In fact, it's a mathematical truism that anything that is a periodic movement can always be represented by circles. So something that we thought is, here's Fourier, by the way, and he was the first one to prove that this is the case. And so something that we thought is a physics law actually just turned out to be a mathematical truth. Always the case. So, of course, Kepler's laws eventually got accepted as a better model. What I'm trying to point out is the following thing. Science seems to go the following route. During a certain phase, there is an increase in the number of parameters that a model has, and then eventually something revolutionary happens and the number of parameters goes down. This is important to understand the thesis I'm going to try to present, right? As the epicyclic models became more and more complicated to precisely match the movements of the planets, we require more and more parameters of all of those cycles. Today, we would call them Fourier coefficients, right? We require more and more Fourier coefficients to match the data more and more precisely. So there was an explosion in the number of parameters that people were using. And people were saying, hey, we need to capture more data so that we can train more parameters. Okay? Imagine this is all happening 2000 years ago. It's all happening 2000 years ago. We need to capture more data and literally like hundreds of astronomers were capturing data over lifetimes to try to create better models. And then someone said, no, here's a model. It requires only 3 parameters, and that's Kepler's model. So model parameters go up and then they go down. Okay, this has happened. This is not the only case. Okay, by the way, Newton came with Newtonian physics and said, well, no, I'll reduce the parameters further. There's only one parameter now, the universal gravity constant. Capital G is the only parameter. That needs to be captured from data. Everything else is explained, including Kepler's law. Everything is explained by this model. So you see, parameters go up, parameters go down. So this has happened not only in astronomy. There are examples throughout physics and chemistry, at least, that I could go on citing about model parameters increasing and decreasing. Okay. With that, we come to large language models. Large language models are, of course, model parameters. All of us, this is all in the news now. Did you ever imagine that model parameters, something that's somewhere inside back propagation, would be in the news? But it's in the news. Hey, I have a 5 billion model, I have a 10 billion model parameters. So, of course, this started most recently with the attention is all you need paper, less than 10 years ago still. And then OpenAI came up with ChatGPT. ChatGPT became famous. Everyone started using ChatGPT. We loved it. Eventually, lots and lots of people got into the fray. And we have what we today call all of these large language models, chat models, whatever you want to call them. Of course, the race currently is what? Is capturing more and more data to train more and more parameters, right? We're still doing that. And we're saying, oh, that country is winning the race. They have more data, they have more training infrastructure, they have more parameters. We can't do it. Oh, that's what we're saying. And of course, in the phase we are in, that is correct. And feeling sad is also correct. But my talk today is about the future of linguistic technology. And so we have to start wondering, does that happen? And if so, when does it happen? So it turns out that currently these large language models, to be able to speak human language, the only way we have figured out is to build these, super intelligent, all knowledgeable wonder machines. By the time they can start speaking, they are like super duper PhDs, bad PhDs, but super duper PhDs in every field. That's the only way they can talk human language, which is very inhuman if you think about it. All of us, many of us, we don't have our PhDs, but we didn't require our PhDs to start talking, did we? Right? So whatever this is something quite different than the way human intelligence works. So how can a model that is so intelligent be so stupid? Right? I mean, you have all has everyone interacted with large language models, ChatGPT, whatever. Yes, you have. Right? Have you ever had this experience? Oh, my God, this is so intelligent. You have thought that. Have you ever thought, my God, this is amazingly stupid? You have all thought that, right? How is this happening? How is something that is so incredibly intelligent, so incredibly stupid at the same time? Okay? And one of the reasons is that we as humans misjudge the vastness of training data and the extreme recall ability that we have given these models. These models are literally trained on every textbook, on every answer, and there are like 10,000 people sitting inside feeding it new information of everything that anyone could ever ask. And it's trained on that. And we misunderstand what training means because of that word. We think it's trained like humans are trained. It's not. It actually has the ability to remember all of that. Just the number of parameters it has, it can remember 100 times the size of Wikipedia. Okay? So many of the times when you think it's intelligent, it actually knows the answer. Okay? It's just like the internet basically. Yeah. Except that it can reproduce the internet in poetry. So I'm not saying it's useless. It's amazing, whatever it is. But it's not like a human being at all. The other thing I think that causes us to misunderstand what large language models are is because they're trained to be engaging to human beings. Why? Because engagement is key, because engagement causes monetary benefits. And so they're trained to be our friends. They're literally trained to be our friends. And so both of these things together cause a kind of anthropomorphization where we start to think of them as human beings, and then we attach to them that extreme intelligence, and then we start wondering how is it also so dumb. Okay. So let's talk about how AI is distinct than humans. First, something that AI can do that we cannot do. Easy replication. Once you get a model, everyone gets that model. You can scale it on the cloud. You can have 20,000 of them. And that is the benefit or the economic benefit of AI, right? I trained myself for almost 50 years now on mathematics. I don't have an easy replica of myself. If I had another Udayan, I'll have to train him for 50 more years, right? So that is, they've been hands down over humans on that. But let's look at where humans are still doing better and much better. There's this observation called poverty of stimulus. Now I'm coming to language. It turns out that human beings can pick up language just by listening to a few hundred sentences. It's called the poverty of stimulus. Okay. I mean, think about babies. You have all observed babies. You have all been babies. You don't remember that, but you have observed babies in your life. And I mean, how much have they heard? They have not heard the entirety of Wikipedia. They have heard maybe a few hundred sentences, and they start talking and they start making grammatical sense. And everyone has been wondering, linguists have been wondering how that might be happening. This famous linguist, his name is Noam Chomsky. He is the one who observed this, the poverty of stimulus. Of course, Noam Chomsky is considered the father of modern linguistics. He himself cites Panini as the old father of linguistics. Panini is the Sanskrit grammarian who built the first idea of a context-sensitive grammar. Chomsky built on top of that. So let's talk about the poverty of stimulus idea. Now, Chomsky thinks that this poverty of stimulus, this, being able to pick up a language with only a few hundred sentences must be happening because human beings have a language instinct. So we have an implicit language function fit inside all our brains. And so we need to train it with only a few hundred parameters and we start working. Okay. There's a common model in all of us, which needs to be just fine-tuned for us to start speaking a particular language, is one hypothesis that Chomsky proposed, that language instinct hypothesis. There are other observations that also satisfy this language instinct hypothesis. For example, how many here are polyglots, which means speak more than one language? It would be hard to be in India and not be a polyglot. So 2, 3, 4, maybe someone 6, 5, I don't know. So we, as polyglots, do you realize that if there are two polyglots who speak the same set of languages, we start speaking in like a language which only the two of us will understand, and we start mixing sentences. No one taught us in our history to mix sentences, but we implicitly understand how two languages can mix. And we come up with hundreds of patterns of mixing the two languages, which is another observation that would fit the theory that maybe there is a universal language and specific languages are just specializations of that universal language. Okay. But I am going to present an alternative hypothesis. I am going to claim that it's not something that we are programmed with. This so-called universal language is not something that we are programmed with. This universal language might actually be a structural limitation of the problem of language itself. Language is for communication. And if it is for communication and we figure out what are the implicit limitations that anything that communicates between human beings must satisfy, maybe all of those limitations together give a much smaller degree of freedom than what we have been assuming language can do. And so maybe it's not something that fit in our brain. Language itself as a problem has a smaller, computational variation than we earlier thought. Maybe that's my alternative hypothesis, right? And to give you again, I have to give examples from other fields because this is all undone right now. So, Noether, greatest mathematician, one of the greatest mathematicians of the last century, came up with what's called Noether's theorem. Before her, physicists were finding all of these invariants like, oh, mass is always conserved, energy is always conserved, this is momentum is, oh, they were coming up with more and more things that seem to be conserved. And Noether said, oh, hold your horses. This is actually happening because of a structural limitation. It is actually symmetries of the universe that are showing up as conservation properties. And symmetries of the universe are just like, space is the same everywhere, time is always the same, physics laws do not change. If you look in any direction, the laws do not change. So basically, it's like a lazy God hypothesis. God didn't take too much effort, just made everything look the same. Okay. And that is enough to come up with all of these conservation properties. And so it's a structural limitation. Okay. So I don't know what the structural limitations are, but I'm going to propose one structural limitation. Imagine our brains are actually probability machines and are training themselves to detect probabilities and probabilistic patterns in language. Okay. Now, here's the thing. Did you encounter the same environment as I did when I was growing up? No. Did he encounter the same environment as you? No. Each of us encountered a very different environment growing up, which means the probabilities fixed in our brain must all be different. And they do show up in what fact? In the fact that we all speak slightly differently than each other. On the other hand, we all seem to understand each other well, right? And so there must be a limitation in the way we produce speech such that computationally our brains are already processing how can I say something so that the maximum number of people with different probabilistic models still understand what I am saying. And that's a possible structural limitation. And that means that probability training need not be done to the level of accuracy that we are trying to do right now. And we might still get very good understanding of language. So now with that, I am going to talk about opportunities for research. You're all researchers, you're doing your PhD, you have done your PhD. So how does all of this, the idea that maybe number of parameters have gone up but might be going down, and the idea that language might be a more limited problem than we have assumed till now. How does that help us come up with new avenues for research? So, the first important opportunity that all of you as researchers should be trying to target is how humans work remains unsolved. Okay. We are nowhere near understanding how human beings are acquiring language. Is that an academic? Maybe it's an academic problem. But as academicians, we should be interested in academic problems. So that remains unsolved. And that is your first big opportunity of trying to solve some big unsolved problem still remaining in the world. But a more specific thing that you can do, and I think that goes towards solving the first problem, is always try to reduce the number of parameters that your model is using. We are going in the opposite direction. We are trying to get more accuracy and using more parameters to get more accuracy. I am claiming that, please try to get the same accuracy with less parameters or more accuracy with less parameters. And that's the direction in which new research directions will emerge, right? Or eliminate parameters entirely. I'll give you some quick examples from our work at Oneirix Labs. SimSpell is a spelling mistake correction algorithm, which is the highest downloaded algorithm for spelling mistake correction. We built an algorithm that beats SimSpell by 7% in accuracy. My talk is not actually a mathematics talk, so I'm not going to tell you the theory itself. But here's an interesting part. How many parameters do you think our new model FathomSpell has that are trained on data? Shall I tell you? 0. 0. Okay. It has got 5 parameters, but they were not trained on data. Why? Because I believe that language should not be very extremely dependent on the probabilities themselves. So if I get the probabilities approximately right, I should get a good enough model. Okay. And we beat the incumbent model by 7% with 0 parameters. Okay. And another idea, why should we do this? If you do something like that, then after that you can start imagining, oh, how could I augment this further with machine learning? Now that I have already gotten 87%, can I go to 95%, 98% by adding a little bit of machine learning? Not a billion parameter machine learning, but maybe a 20 parameter machine learning model. And why would that be great? Because a 20 parameter machine learning model is likely to be much more significant than a billion parameter machine learning model, which is likely to hallucinate. Okay. So the second opportunity for research for all of you is reducing number of parameters. Other opportunities of research are doing non-machine learning algorithms with large data sets. The large data sets have come about to train machine learning, but now they exist. Now that they exist, we can start imagining what can we do with these large data sets without using machine learning. And maybe there is a whole new class of algorithms that we can build based on these things that now exist, which are these huge data sets, right? And I'll give you an example. We are building an algorithm called Fathom Graph, which basically is a natural language query engine to database. These things already exist, but what most people are doing is taking a natural language query, converting it into a database query, and then trying to ask a database, and the database will respond with data, right? Now, this has inherent limitations, right? Language, people figured out that language is hard because there is a lot of ambiguity. And then they thought that language can become better if we remove the ambiguity by using contextual information, by context. And there are a lot of attempts at that in the 80s and the 90s to give language models context. If you are trying to query a database using language, where is the context? It's inside the database. The data inside the database is the context for what you might be asking. And so instead of thinking of these as two separate fields, if you can design entirely new algorithms, which are not a separate database query engine and a separate language parser, but something that is at the same time a single algorithm that is both, then you can build algorithms that um, understand the query much better and respond with accurate data. And we are showing this product will be released in the next few weeks. You can do it more accurately at a cheaper cost and faster than large language models. Why? Because if the data changes, the large language model has to retrain itself, whereas this algorithm just accepts the change in data like a database does, and in a few milliseconds, it's ready. Okay. So now, again, this is not a math talk, so I'm not telling you the algorithm itself, but these are the opportunities that all of us should be going against, not the same direction in which people are going. Okay. These are the opportunities that will be the next amazing thing in research. Okay. Uh, Finally, see, LLMs are being augmented, right? So, for example, first we thought, oh, LLMs are so smart, they will do anything. They'll do everything. Then we said, oh, they are not smart enough. We will increase their size and make them smarter. That reached its limit. And then we started augmenting them using ideas like RAG and MCP, and new ideas come up every day. Okay. I believe that LLMs being augmented is the first step to LLMs being replaced. Because eventually the intelligence will all be in the augmentation and you won't need the large language model at all. Especially if you had a language understander that goes with all of this augmentation, you won't need a large language model eventually. And that would be a much better world because it will be a world which hallucinates less and does our bidding more precisely. So that I think is the future of linguistic technology, of computational linguistics. I hope I was able to show you some direction in which all of us ought to be going. So let me just say that to do this, we have to put the philosophy back in our PhDs. We have to become philosophical and try to understand really at the core what we are trying to do. And doing that, maybe we will make intelligence computational again. Thank you.
Thank you, sir. Thank you so much for your wonderful talk and the insight on the intelligence. Uh, I would like to give the phone to